We all use computers every day, but sometimes computers fail us, and this upsets a lot of people. What we'd like is for our computers to be smarter and more user-friendly, so some people think we should try to make them more human. This would involve making computers think more like people. But to do this, we first need to understand how humans think and how our brains work. First though, let's look at computers as they are today. Despite everything they can do, they're pretty simple. They take some inputs, perform some calculations, and produce some outputs. The human brain, however, is extremely complicated, and a lot of very smart scientists are still struggling to understand how the whole thing works. One thing we have known for a while though, is that the tiniest components of your brain that makes it think and do smart things are special cells called neurons. Your brain has billions of these neurons, and they talk to each other using electrical impulses to create what are called synapses. This mass of synapses is what is responsible for making your brain think and have a consciousness. Some computer scientists had the idea that we can make a computer that is modeled after this system of neuron connections. They called their idea neural networks. The idea behind neural networks, or neural nets for short, is that we have nodes that have some connections between them. This is similar to the neurons in your brain and the synapses they form. To get a neural net to do something, we trigger a node with some input, and that node in turn triggers the nodes it is connected to. But this alone is not very useful, so we usually organize the neural nets in a way that makes it easy to produce good results. Since we're used to the computer model of computation, we like to have well-defined input and output nodes. We also like to have directed connections, so that we know which way information is going. Not only that, but we want our connections to have different values. That is, some connections should be more important than others. Here the connection values, called weights, are represented by the thickness of their arrows. The purpose of having different connection weights is that it allows our nodes to behave more like real neurons. When a node is stimulated by two different nodes, it can decide which of the two is more important to it by their connection weights. Here, nodes A and B have been given the values green and orange, and they try to pass on these values to node C since they are connected to it. Since the connection weights between B and C is much larger than the connection weight between A and C, node C decides B is more important to it and takes its value. More often though, we design nodes to take a sum or an average of the nodes triggering it. Here, node C takes a sort of yellow color, but notice the shade is much closer to orange than it is to green, since node B's connection weight is large compared to node A's. In some cases, we'd like for our nodes to be able to decide whether they want to accept their triggers at all. So each node gets to think about what it will do. To decide, each node is given what is called a transfer function to judge its inputs. Since in the real world computers treat all data as numbers, the transfer function is a math equation. It's usually not that complicated. After the node makes a decision, it sets its value, and then it can trigger the next set of nodes with that value. Choosing whether or not to accept the triggered value is most useful for the output nodes, since these are the nodes that produce the results that we actually want. Usually though, the transfer function will return a value that is a combination of the node's current value and the trigger value. So using the connection weights and transfer functions, the neural network takes its inputs and produces outputs. This is the same task that a computer would do, but it's done in a way that is similar to the way neurons work. Since the input and output nodes are the ones that matter to us, we consider the nodes in the middle hidden nodes. They do most of the work, but get the least credit. Now that we know the basics, we need to ask some questions. One of the most important questions is, how are the connection weights determined? Well, it turns out the neural networks can learn them. Does this make neural networks smart? Sort of. But it also turns out that the neural networks are very slow learners. Very slow learners, as we'll soon see. But the question is, how do they learn? It's done through a process called backpropagation. We start with random connection weights. Then, for a given set of inputs, we decide on a set of desired outputs. Using the random weights, we first let the network calculate some outputs. Then, we compare the outputs that the neural net calculated to the desired outputs that we defined. Since we gave the network random weights, we obviously cannot expect the two outputs to be equal. So we find their difference. We call this difference the error in the network. This is difficult to illustrate with colors, but you'll have to trust me that I did it correctly. For an easier to follow example, I've given each node a numerical value. You can see that we find the error by simply subtracting, and then we can have negative errors as well. Now that we have the errors, we need to adjust the connection weights to try to produce smaller errors. This is where the backpropagation comes in. The output nodes tell the hidden nodes they are connected to about their error, and together they decide on how to adjust the connection weights between them. The new weights are calculated using an equation based on the old weight, the node's input value, the error, and something called the learning rate. We'll get back to the learning rate later. With the weights adjusted, the hidden nodes calculate their own error using a similar formula to before. Then, these nodes with their newly calculated errors push the errors back through the hidden nodes and adjust the weights behind them. This goes on until all the weights have been adjusted and all the nodes have been assigned an error. The idea is to determine which nodes are most to blame for the error in the output and try to adjust their weights the most. Now that all the weights have been updated, the network tries out the original inputs again and tries to calculate some outputs. The calculated outputs should be closer to the desired outputs than before, but there will still be some error. So the whole process is repeated again, and again, and again. Remember how I said the neural nets are slow learners? Well, the neural network has to do all that for each different input set, and there's usually a lot of those. But the idea works, and eventually the network will produce the desired outputs. To try to produce the desired outputs more quickly, we can try adjusting the learning rate. And we can change the number of nodes as well. But it will still take millions of attempts for the neural network to get the desired output for even a simple problem. So, can neural networks make computers think more like humans? Probably not, but it's a good baby step. Well, that's my presentation on neural nets. I hope you liked it, and maybe learned something as well. Feel free to email me if you have any questions. Thanks for watching.